Hello, I'm recording this video to prepare you for the new topic, which is Macaulay method to calculate deflection and rotation in any point of the beam. From structures 1, if you remember, or if not, you can open the model page and review the part that we discussed about maximum deflection in designing beams. So I provided you some tables for different beams and also different loadings. And so from those tables, you could find maximum shear, maximum moment, and maximum deflection of the beam. So here is an example. You can see a simply supported beam with the UDL, uniformly distributed load. And here is a formula to calculate the maximum deflection of in the beam, which happens at the center. Here is another formula to calculate the deflection in any point of the beam. When we say deflection, we mean sagging. So if it is a straight beam, if you apply a load on it, it will deform. So this displacement, we call it deflection of the beam. And also when it happens, here is, as you can see, here is a rotation. So we want to see how we can calculate this rotation as well as maximum or maximum deflection or deflection of any points in the beam. What if the beam and that special loading that we are interested in is not in the table? So in this case, we use Macaulay method to calculate the deflection and rotation of any point of the beam, as well as the maximum value in order to use it in our beam design process. Before starting this method, we need to recap some information that you need in this method. For example, you need to be able to draw the deformed shape of the beam. And also, you need to be able to integrate and double integrate of the formula or from the equation. You need to be able to use boundary conditions. And also you need to remember how to calculate moment of inertia of a section. We start with deformation of a beam. Here you can see we have a simply supported beam. We have upward concentrated load and downward concentrated load at C. So here is the moment diagram. So if you remember, we said wherever you have negative moment, that would be upward curve. And if you have positive moment, that would give you downward curve. And wherever you have a zero moment, which is here, it is the inflection point. It means the curvature changes in that point. As you can see here, which is a negative moment, we have upward curve, and at the inflection point, we changes the direction of the curvature, and that would become downward this way. For this beam, which is cantilever, again, we have a concentrated load P1 upward and concentrated load P2 downward at the end of the beam. Here is the moment diagram that you should be able to draw it by the knowledge that you already have. And as you can see, initially we have positive moment, zero moment, which is inflection point, and then negative. So as you know, initially, because it is cantilever, it starts with zero slope. So we have no rotation, no displacement. So it starts with horizontal line, and initially we have downward curve, and inflection point changes the curvature and become upward curvature with negative moment. Let's practice more. Here we have 1, 2, 3, 4, 5, 6 beams with different loadings. I want you to draw the deformed shape of the beam by heart. Okay, so I haven't provided you any diagram. I just want you to use your common sense and the rules that you already know. For example, here the rotation is 0, the displacement is 0, so this point is fixed. Here is also fixed. This points are fixed, they don't move, as well as these two, and also we have a 0 rotation here as well. So stop the video for a few minutes, take your time, draw the deformed shape of these beams, and then we discuss about how to draw the deformed shape of the beam. Please do stop the video and try your best, and then continue watching. Okay, here you can see in the beam A, we have only one concentrated load applying to the beam. So the common sense say that it deforms downward, and the curvature would be downward. And here there is 0 displacement, and at B we have 0 displacement and 0 rotation. Here in, B is here. So you have UDL on top of your beam, initially at A and at B, because there are fixed support. You have no rotation and no displacement, but then you have downward curvature. At C, there is a moment which bends the beam like this, and it is a pure moment around the beam. At D, as you can see, we have a force here. It pushes it downward. We have a hinge. And here, because there is no force applying in this part, it is a straight line because it acts like a truss member. We have two pins at the end and there is no loading during a beam, so it stays straight. However, this part, it starts with zero displacement, zero rotation, and then goes down. In here, E, as you can see, we have only one force applying to the beam. So here, it goes down, and at the hinge, you can see if we have hinge or not, it doesn't make any difference because here is the point of inflection. So at the point of inflection, the moment is zero. And in this case, the curvature changes as well. It was downward and it turns to upward. So you cannot notice the hinge here. Here you can, at F, you can see we have UDL in the middle. So if you push the beam downward in here, because it is continuous, you have to continue the line and then go back to the fixed point at D, same as the other part. So you push it downward and then you have to continue here because it is a continuous beam, you cannot break it. So it has to goes up and then come back to the support. Try to figure out why and what the reason behind what I said. And if you have any question, ask me tomorrow. Now we want to draw the deformed shape of these two beams as well as these two frames. In here we have pin and pin. Here these two are fixed. Both are fixed. So you have no rotation and no displacement in these two supports. But here you can rotate the member, but you cannot move it, okay? Just pay attention at the rigid joint like here, you have to keep that joint at the right angle. So if it moves, this one needs to bend, you have to bend this one in this way to keep the right angle. The right angle needs to keep constant. So if the joint turns, they join both side of that joint rotate together. That would be like this, okay? Now, by knowing this information, I would like you to stop the video and try to draw the deformed shape of these beams and the frames. Here is the answer for part A. As you can see, I started with zero displacement, zero rotation. It is a straight line. and then it goes down. Because of this force, it pushes it down, so it goes down, but it has to come back to this support because this point is kept by that support. And because the beam is continuous, so you have to continue going up, but you have to come back to the support again. Think about it to see if you can make sense of it. For the second one, as you can see, we have a force here, it pushes it down. And then because it is a continuous beam, it has to, the slope has to keep going. And then it has to come back because of the support. And if you go smoothly down, you cannot break the line. You have to move smoothly. You cannot just break it. Because it is a straight beam, you just can move it like this. You cannot break it. So here again, if you continue that slope and go down, again, you need to come back to this support. For the beam, this is a pin, so we have a rotation at the pin because this joint pushed forward, so it moves like this, and then you have to keep the line, you have to keep the angle at the right angle as it is, and then go up and down. It's a bit tricky here. So if you again go here, you have to keep the right angle and again come back to the pin support. For the other one, as you can see, I kept the straight line at the supports because they are fixed. We don't have any rotation. And then you need to bend this down for the beam and then keep the right angle at both ends and draw the line like this. Just think about it and ask me if you have any questions tomorrow. Here, I want to remind you how to integrate different formulas. Here, if you have a fixed or constant number, which is A, and you integrate it once, that give you A times X plus C1, which is a constant that you need to calculate later. Don't worry about this, just write it down as C1, okay? So for if you integrate constant, you will get constant times X plus C1. This X can change, it is variable. If you integrate twice of A, you will get A. And just, you can also assume you integrate once more this phrase. So you have AX plus C1. If you integrate it, you will get AX squared divided by 2 plus C1 times X plus C2. Here is how to use, how to integrate a variable x. So if you integrate it once, you will get x squared divided by 2 plus c1, which is constant. And if you integrate this twice, so you will get the x cubed divided by 6 plus c1 x plus c2, which is constant again. So in this part, we just need first integration and double integration. Just practice these two. Here we have integration of x squared. So we have x cubed divided by 3 plus c1. And if you integrate it twice, it gives you x4 divided by 12, which was x4 divided by 4 times 3 from the previous one, plus c1x plus c2. If you have x3, so you will get x to the power of 4 divided by 4 plus c1. And for the double integration, you will get x to the power of 5 divided by 20 plus c1x plus c2. Let's have a look at some examples. If you are confident, you can stop the video and try to go through them and then check your answers with the video. Otherwise, you can watch the video, continue watching the video and figure out how to deal with this terms. Okay. First, we have 3x plus 5. What we do is, for the first integration, you have x, so it gives you x squared divided by 2. And you have a constant, so you just multiply it by variable x plus c1, which is a constant. If you integrate it twice, it means integrate this term. So as you can see, I put the answer for the first integration here, and I integrated once more. So you have x squared, so it gives you x cubed divided by 3, and you had 2 before, so that would give you 6 plus 5x, x would turns to x squared divided by 2 plus a constant, which turns to constant c1 times x, and you have another constant c2. Let's have a look at the second example. It is 5 times x squared minus 7. So for the first integration, we have 5 times x cubed divided by 3 minus 7 times x plus c1. If we integrate it once more, then we have 5. It's x4. Sorry, this one is x4. It's not x3. So we will get 5 times x4 divided by 12 minus 7 times x squared divided by 2 plus c1x plus c2. Let's have a look at this one, which is very interesting, and we may use it a lot. So here, if you integrate it, you have x minus 2. So my suggestion is do not expand this bracket. Just keep it as it is. So if you have 2 times x minus 2 squared, do not expand it. Just behave it as a single variable. So just you can consider this one is your variable, like assume y. So that would be 2 times y squared, for example, because we do not want to touch that bracket. Whatever inside that bracket, leave it alone. So that would be 2 times x minus 2 cubed. So it was squared turns to cubed divided by 3 plus c1. If we want to integrate it once more, it gives us 2 times x minus 2, which was inside the bracket. We just keep it as it is, to the power of 4 divided by 12 plus c1x plus c2. c1 and c2 are constant that we just keep them like this for now. Then we will learn how to deal with them later. The last one, I think it was the last, is something like this. So you don't need to panic because you can behave each part as a single term separately. Don't worry about the whole stuff. I mean, if you have 4 times x minus 4 squared, you have a bracket, keep the bracket, do not expand it, and behave it as a variable. So that would give you 4 times x minus 4 cubed divided by 3. And the next term would be 2 times x minus 1. So it turns to 2 times x minus 1 as a package, squared divided by 2. And then the next one is 6 times x. It becomes 6 times x squared divided by 2. The last one is minus 8. It is a constant, so that would be minus 8 times x plus c1, which is a constant. Now for the second one, second integration, again, we deal with each term separately. So we have this term, 4 times x minus 4 cubed divided by 3, that would turns to 4 times x minus 4 to the power of 4 divided by 12 plus 2 times x minus 1 cubed divided by 6 plus, for this term, 6 times x cubed divided by 4, and for this term, 8 times x squared divided by 2 plus, you have a constant here, so that would be plus c1x and another constant, which is c2. Before going to boundary condition, or just, yeah, let me explain about boundary condition. So boundary conditions come from the different situations that you have in a beam. For example, if you have a roller support, it means the displacement is 0. So it is a boundary condition. If you have pin support, again, you have displacement equal to 0. For beams, we don't really care about horizontal support reactions. So as you can see, either a roller or pin provides you only one boundary conditions, which is the displacement. It means the displacement in vertical direction equal to 0. And also for the fix, we have two boundary conditions. So one of them is the displacement equal to 0. The other one is the rotation equal to 0. So if you have a fixed support, it provides you with two boundary conditions. Just remember, as I told you, if you have a rigid joint, the rotation in both sides are equal because they move together and the angle here stay constant. So the rotation on the right-hand side must be equal to the rotation on the other side. If you have a pin joint or hinge, internal hinge, it means the rotation is not equal. However, the displacement is equal. So it provides you with one boundary condition, which is displacement on the right-hand side is equal to displacement on the left-hand side. Here is a recap for the moment of inertia. So we have different formulas for standard beams. So for the rectangular shape beam, we have a moment of inertia around x-axis equal to bh cubed divided by 12, and the square, and for the triangle, we have this formula. For the rod or solid circular cross section, here is the formula, and for the other ones also we have different formulas. Here is a reminder that for standard cross section like I-beams, channels, and other standard cross sections, in New Zealand, we have different tables that you can use to find the moment of inertia, and you don't need to calculate them by hand. Okay, now let's learn how to use whatever we learned so far to use the Macaulay method. Step 1, you need to calculate the support reactions. So as you know, this step is always the first step that you take in all the analysis that you do. The second step is just assume we have this beam with different loadings, and you have UDL loading somewhere on the beam. It can be starting from the beginning, or it can start from the middle of the beam, or it can be at the end of the beam. In case that you have a UDL on your beam and it doesn't continue to the end of the beam, you need to continue that UDL from where it stops to the end. And also you need to apply another UDL in the other direction to cancel this part out, because this part does not exist. This UDL doesn't exist. So you need to cancel this out by another UDL in opposite direction. We use this method to make the procedure much easier. If we don't use this, that would be a bit too time consuming and you need to do a lot of calculations. But for avoiding that, it is required to continue the UDL to the end of the beam and then apply another UDL in opposite direction and equal value to cancel that out. The third step is to have a cut. You need to have a cut through the beam wherever all the loading has been applied. So as you can see, we have one loading at the end of the beam. So you cannot cut after that because it is at the end of the beam. So just ignore the force which applies at the last point of the beam at the end. So ignore this part and just cut through right behind that point, like this. When you cut through point B, you would be able to include all the loading which has applied to your beam, and you will see all of them in your equation. So it is necessary to make sure that your cut is wherever all the loading has been applied from the beginning to that point. So after this B, we don't have anything special applying. Like for example, UDL, we already have UDL before this point, so we will see it in our equation. However, we cannot include the last point force, and we are not worried about that. If you remember, we discussed about cutting through a beam or cutting through any structural element. So wherever you have a cut, you will see three different reactions coming out, which are internal forces. So if you remember, I said that would behave like a pipe which the water or fluid passing through. You are not able to see it, but as soon as you cut it, all the water coming out, and you would be able to see what fluid going through that pipe. So it behaves exactly like that. So if I cut through point B, then I would be able to see reaction internal force, which is in vertical direction, vertical force in horizontal direction, internal force in horizontal direction, and internal moment. So I have three internal forces at that point. So I have mx. So what I do in the next step, assume that from the beginning, which is here, to B is the length is x. And you need to drive the equation for mx based on that x parametrically. So here is the beam from A to B. The length is x because B is any point in here. It can be any point. It's not an exact location. So we don't have the exact number for x, and we don't want to have exact number for x, okay? We want to drive the equation parametrically and find mx, which is the moment at B based on x, which is the variant. Okay, I would like to give you some example, since here you don't need to worry about the rest. We will discuss about the rest tomorrow. Here, consider we have a beam AC here with a concentrated load applying at B, which is 80 kilonewton. The length of the beam, total length is 8 meters. It is meter in meter. And here is the cross section in millimeter. So the dimension for the cross section is in millimeter. So it is 200 millimeter and the height is 600 millimeter. So now what we need to do, what was step 1? Calculate the support reactions. Here, as you can see, the beam is symmetrical. The loading is symmetrical. So you can find AY and XY from this symmetrical situation, which is 40 kilonewton and 40 kilonewton. Then for step 2, which was about UDL, and in this case, we do not have any UDL applying on our beam, so we are not worried about that. So we just skip step 2 and go to step 3. Step 3, we want to take a cut through the beam where all the external forces have been applied. So if there is a force at the right end of the beam, ignore that in this stage. So it means don't worry about reaction at C. So any point between B and C, you can cut through the beam, and that would be the ideal location. So here you can see I draw the free body diagram for a, just call it J, AJ. So you can see the loads applied on this part of the beam is support reaction at A, force 80 kilonewton at B, and we have horizontal, vertical, and the moment at J. As you can see, I didn't show this horizontal vertical. It means I'm not worried about that because what I'm gonna do, I'm taking moment about point J, which is here. So if I take a moment about point J, the forces, vertical and horizontal forces at point J will pass through that joint and they don't create any moment. So as I told you, we assume the total length of this part is x. So it means AB stays 4 meters, but BJ is x minus 4 meters. Okay. So assume this free body diagram, take a moment about point J and find mx parametrically based on x. So that would be mx. So as you can see, counterclockwise, I assume it is positive. It is up to you, doesn't matter. So I assume counterclockwise positive. So that would be mx minus 40 times x plus 80 times x minus 4. So that would be mx minus 40 times x plus 80 times x minus 4. As you can see, now I have some of the moment about point J equal to 0 and these ones I will correct it. So it is AJ, the point J, which is the point that we cut through. AJ, and we took a moment about J. So now what we do is to bring mx to the other side or bring the other terms to the other side and write mx equal to that equation. It was pretty standard, straightforward so far. It was what we usually do in analyzing the beam. So the only thing which is different is to drive the equation based on variable x and keep the x in your equation. Step 5, we want to integrate this twice. Once gives us the rotation in any point of the beam, and the second one gives us deflection in any point of the beam. So you should put 1 divided by EI. It is in the formula. So you have to put 1 divided by EI and then integrate mx that you found from previous step. So that would be 1 divided by EI times this integration. So if I want to integrate this part, that would be 40 times x squared divided by 2 minus 80. So as you can see, we have a x minus 4 and I keep it as a package or as a, and I do not expand it. I don't say 80x minus 80 times 4. Just keep it as a bracket. And it gives you minus 80 times x minus 4 squared divided by 2 plus C1. For deflection, what we need to do is to integrate this term, which is our rotation, once more. So that would be 1 minus EI, and integrate this term. So that would be 40 times x cubed divided by 6 minus 80 times x minus 4 cubed divided by x plus C1x plus C2. Okay? Now what I want you to do until tomorrow to make sure that you watch the video is I want you to go to the Moodle under the deflection Macaulay method tab. Here is the exercise. If you open it, you will be able to see 3 exercises. I would like you to drive to find theta, which is the rotation, and also delta, which is the deflection of the beam for 1 and 2. Just leave 3 because 3 is a bit more complicated. Just drive mx for this beam and this beam, 1 and 2, and find theta, which is rotation based on x, as well as delta based on x. It means whatever I've done in here. So I've been through step 1, step 2, which was UDL that I didn't have, and step 3 to cut through the beam. Step 4, drive the moment about that joint, and then integrate this once to find the rotation, and integrate it once more to find deflection. Okay. Let me explain this part as well. So here you can see in this question, we have a UDL in the middle of the beam. So the first step is to find the support reaction because it is symmetrical. AY and CY equal to 40. And in step 2, because we have UDL, as you can see, I continued the UDL to the end of the beam, and also I applied another UDL upward. So this 20 kilonewton per meter is downward. I apply another 20 kilonewton per meter upward in the place that we didn't have any UDL to cancel that out. And then I cut through somewhere between B and D here. As you can see, we have UDL upward, downward, as well as the UDL that I applied myself upward. And then just behave it as a normal beam. You have a free body diagram and find mx based on x. So here you can see we have mx. Try to drive it yourself before watch the rest of the video. So try to drive mx and then watch the rest of the video. Okay. So you can see here we have mx minus 40x, which is the support reaction at A, plus 20 times x minus 2 times x minus 2 divided by 2 minus 20 divided by 2 times x minus 6 times x minus 6 divided by 2. I can't remember if I said, okay, that's, okay. So here, so as you can see, we have 40 times x, the total length is x. We have 20 times x minus 2, which is this length, times x minus 2 divided by 2, which is from the center of this part of UDL. And we have another UDL minus 20 times x minus 6 times x minus 6 divided by 2, which is the center of this UDL. And it gives you the equation. What you really need to be aware of is do not replace the UDL with concentrated load. You can do it only in the first step to find the support reactions. After that, you have to keep the UDL as a UDL. As you can see, if we cut through here, if you didn't keep this UDL, you wouldn't see any x2 in your equation. And everything will go wrong in this method. So you have to keep it UDL until the last step. Do not replace it with concentrated load, okay? So now we have mx, which is the moment at that point, which we cut through the beam based on x. And we can drive the theta, which is the rotation, by 1 divided by EI times integrating mx. And if you integrate it another time, that would give you the deflection. Okay? So please spend some time for this part and do the same thing for a question 1 and 2, and we will discuss about it more tomorrow. Thank you very much, guys. I hope you have a good day. See you tomorrow.